A Lucas-Fibonacci amplifier related to golden amplifier is shown here with V in at the input of circuit and V out at the output, and with infinite resistive network, as you can see here because of this ellipsis, both up and down side of the circuit. We want to show that V out, appearing at the output of circuit, is equal to rad 5 or square root of 5 times V, and basically this circuit with infinite resistive network is realizing a finite gain of square root of 5. Okay, how's that possible? I want to show that this very interesting circuit is capable of generating basically the locus numbers here at the output of the op-amp number 1 and the Fibonacci numbers here at the output of op-amp number 2. And therefore, just before analyzing the circuit quickly, that is possible to do it very fast, I just want to remind what is the relevance of Fibonacci and what is the relation between Fibonacci and locus numbers. So if n is index, which is a natural number, 0, 1, 2, 3, 4, it's well known that Fibonacci number n is simply the sum of the two values before, like 0, 1 give you 1. And then after that we have 1 plus 1 give you 2. And then we have 1 plus 2 give you 3. Now, interestingly, if you consider locus numbers, they are the summation of corresponding Fibonacci number alternatively. So for example, 0 plus 1 give you 1, and then 1 plus 2 give you 3, and then after that 1 plus 3 give you 4. Also, at the same time, similar to Fibonacci number, for locus number n, we have this interesting property that 2 plus 1 is 3. Then 1 plus 3 is 4, and 3 plus 4 is 7, and so on and so forth. So similar to Fibonacci, locus number n is simply locus number n minus 1 plus locus number n minus 2. So that is very similar to what Fibonacci number generator works. It is shown as a, so the closed form formula for locus number n is also proven that is following this formula, in which the 1 plus rad 5 over 2 is just the famous golden number, so that is golden ratio, and this is the conjugate golden ratio here. So what we want to show, and also before I quickly analyze the circuit, the visualization of locus numbers are shown here that happens in nature and actually in sunflowers. So it's very similar to what the visualization of the Fibonacci numbers is in terms of, again, what's happening in nature and shellfish and also sunflowers. So these formation happen in nature a lot. This is the sequence of Fibonacci number. This is the sequence of locus numbers. What I would like to mention that it is also proven that the limit of locus number n divided by Fibonacci number n when n goes to infinity is equal to constant rad 5 or square root of 5. One other interesting observation is we are actually, for the golden ratio, 1 plus rad 5 over 2, which is roughly 1.618, so on and so forth. It's effectively the answer to the value or the result of this infinite fraction, 1 plus 1 over 1 plus 1 over, and so on and so forth, up to infinity. So there is interesting math going on here. So with that said, let me focus on showing that we are dealing with locus number here, n, and Fibonacci number n here. So for op-amp number 1 and for all op-amps, we make the assumption that the supply voltages, including positive supply and negative supply, are properly connected. So plus VDD minus VDD properly connected. These op-amps are in proper negative feedback, as you can see. So they are in linear region of operation with proper bias, and therefore, because they are in linear region, I can say virtual short is valid for all the op-amps, which indicate that op-amps, as I said, with proper negative feedback in linear region of operation, and therefore the voltage at positive input terminal is the same as voltage at negative input terminal for each of the op-amps, the 3 op-amps that are shown here. Okay, so what's happening? Because of virtual short, because V in is at, let me change the color so that it's easily observable. So because V in is at positive terminal, therefore V in appear at negative terminal as well. And because op-amp are sort of ideal op-amps, practically the open loop gain is infinite, and also there is no current coming out or going into the op-amp. So with that said, there is no current going or coming through the input of the op-amp. So V in is here. Let's refer to, in this scenario, let's just say that V in divided by R is equal to I. Let's name it, so the V in divided by R is referred to as I. So here, the current that is going through this R over 3 will be 3 times that, obviously, because the resistor is 3 times less. So this is 3 times I. That current can only continue going through this resistor. So 3I going through this resistor R, if I just push the R upside so that there is enough space to show you what I'm trying to say, then as a result, plus minus 3V, if V refers to V in, then shows up across this one. So we have, and just to make it nicer here, so V and also V. Okay, so we are referring to V in as V, just to simplify writing, and we have V plus 3V. So as a result, we get 4V here. Now, 4V over R will obviously give us 4I, because we said that V over R give us I. So now 4V over R give us 4I. We have 4I and we have 3I. So if you write a KCL at this node, the result is 3I. If I change the color so that it's observable, we can see that 3I is going through this resistor, that's 3I, and 4I is going through this resistor. So as a result, 7I total. Because of KCL, we have to say that 7I total is going through, so I'm going to write it on top. Okay, so maybe just write it here. So 7I total is passing through this resistor R. And because V is Ri, then the voltage drop across this one will be 7V. Okay, so 7V plus 4V, that would give us the voltage at this node to be 11V. So you can see we are following the Lucas numbers actually with this circuit. See, we started with 4V, so we realized 4, and then after that, after 4, the voltage drop across this resistor is 7, so we got 7. Then we got 11, 7 plus 4 is 11. And finally, we have so on and so forth. So this keeps going on. And with the infinite resistive network, we realize basically at this node, ln, when, of course, limit of ln, when n goes to infinity. So let me just write it here. So at this node, what we are realizing is the limit of ln, or locus number index n, when index goes to infinity. That's what is being realized here. So let's refer to that for now as so that is the gain multiplying V in. So if I just put it here, then it's easier to see. This is multiplying V in, and if I shift this virtual short to this side, so this is multiplying V in at this node. Let's refer to this as Vx. So here, of course, we have a divide by 2 of that because of this simple voltage division across R and R. So as a result, we get Vx divided by 2. So 0.5 Vx. Because we are saying that op-amp 3 is properly biased with the supply voltages properly connected and with the negative feedback that is properly applied between output and input, Op-amp number 3 is also benefit from virtual short, which means if we have 0.5 Vx on the positive input terminal there, we should have 0.5 Vx negative input terminal as well. So 0.5 Vx appears here as well. So I will write it here, 0.5 Vx. Now, look at the op-amp number 2. What happens is via this feedback route, which I'm going to show with different colors. So Vout, via this feedback route, appears at the positive terminal of op-amp number 2. So therefore, what I get is Vout is here. Again, op-amp 2 is properly biased, so VDD, negative VDD is properly connected. As a result, it is benefiting from virtual short, and that means the negative terminal should be Vout as well. So this node is Vout, and let's refer to this current as Vout over R equal to I2. Okay, I2 is going this way. Obviously, it can't go through the input terminal of ideal op-amp, so it has to keep going through the resistor R that I'm shifting upward. So this I2 has to go through this resistor as well. As a result, it is resulting in another plus minus Vout here. So the voltage at this node is 2 Vout. And as a result, there is this current that is 2 Vout divided by R, which is 2 times I2. So 2 times I2 is going through this resistor. Writing a KCL or Kirchhoff current law or law of preservation of current, I2 plus I2 will give us 3I2. So 3I2 is passing through this resistor, resulting in plus minus 3R I2, which is 3 Vout. So what happens is we have 2 Vout plus 3 Vout now, which will give us 5 Vout at this node. And that would give us across this resistor I 5I2. And again, writing KCL here, 3I2 plus 5I2 will give us 8I2. And you can see we keep generating now Fibonacci numbers because we have 1. So 1 Vout, then we have 2. Okay, so we have, let me just get rid of these. Okay, so good. Now we have 2, we have 3, we have 5, we have 8, exactly what we see for Fibonacci number. I'm going to highlight them here. So 2, 3, 5, 8, and so on and so forth. So no wonder at the end we generate Fibonacci n, but similar to what I said before, effectively what we are doing is we are generating at this node the limit of, so it's the limit of Fibonacci number index n when n goes to infinity, and that is the gain that multiplies V out at the input of op-amp number 2. So it's V out that is coming. So, okay, let's refer to this as Vy. So we have Vy here. Vy. Now I'm going to write a KCL at this node. So if I write a KCL here, so KCL or Kirchhoff current law, law of preservation of current, the sum of current going in should be equal to the sum of current going out. So there is this current that is flowing through this resistor, which is I3, should be equal to this current that is going out, because no current can go through the input terminal of ideal op-amp number 3. So I3 should be equal to I4. I'm going to write it here. I3 is equal to I4, and if I substitute for that, I get Vy minus 0.5 Vx, the two voltages across R. You can see that on one side we have 0.5, on the other side we have Vy. So we get Vy minus 0.5 Vx divided by R. So I'm writing a KCL. Kirchhoff current law, is equal to, so that is for I3, and for I4 I have 0.5 Vx, and on the other side I have Vout. So 0.5 Vx minus Vout divided by R. So these two R cancel out, and as a result what I obtain is the fact that just Vout is simply equal to Vx, because 0.5 Vx and negative 0.5 add together becomes Vx, and then minus Vy. But what is Vy? So Vx and Vy can be substituted using the formulas we found. So this one and also this one here. So what we get is this situation. We get, so substituting using the formulas we have for, say, the formula number, say, 1 and number 2. So I can use, and this is number 3. So in number 3, by substituting from 1 and 2, I can write Vout is Vout, Vx is just ln, or the basically locus number times Vn, so locus number times Vn. And we have for Vy, as you can see in equation 2, just Fibonacci number times Vout. So it's a feedback, of course. You can see there is a feedback in this network because we are connecting output to some portion of input via this wire. So no wonder we get to this loopback equation. So as a result, we have 1 plus Fibonacci number index n times Vout equal to the locus number n times Vn. So as a result, I get Vout is equal to locus number divided by 1 plus Fibonacci number times Vn. And when n goes to infinity, basically the size of this infinite resistive networks getting very large. We can approximate this formula by saying it become effectively just so Vout over Vn effectively becomes limit of locus number index n divided by 1 plus Fibonacci number index n. When n goes to infinity, which is roughly the limit of locus number n divided by Fibonacci number n, when n goes to infinity, that at the beginning of this conversation, I mentioned that it's mathematically proven to be equal to rad5. So this number is just square root of 5. And this concludes the proof that I wanted to present, that even with the infinite resistive network presented here, the gain of this circuit is interestingly just a square root of 5, and it has a relation with the golden ratio, because it's well known that the ratio of consecutive locus numbers as n goes to infinity, for example, 47 divided by 29 approaches the famous golden ratio. So that's one of the interesting properties of locus numbers. I hope that this circuit example is helpful.